September 1946. Sir Stafford Cripps, President of Britain's Board of Trade, signs the export license authorizing delivery of 10 Rolls-Royce Nene turbojet engines to the Soviet Union. The Nene is the most powerful production jet engine in the world, 5,000 pounds of thrust, double the output of any captured German design. Cripps inserts a non-military use clause, confident Stalin's metallurgists cannot replicate the mnemonic alloy turbine blades that spin at 2,600 revolutions per minute without cracking. Britain is broke. Post-war debt so severe the cabinet calls it a financial Dunkirk, and the export revenue is desperately needed. Cripps bets Stalin wants peaceful trade. He is betting wrong. March 1947. Cripps approves a second export license for 15 additional Nene engines. The total eventually reaches 55 engines delivered under a commercial contract framed as goodwill between wartime allies. British officials believe the centrifugal compressor design will soon be obsolete. Rolls-Royce is already developing the axial flow Avon for the next generation of fighters. Prime Minister Clement Attlee's cabinet prioritizes export revenue over Cold War risk. 17 Soviet engineers travel to the Rolls-Royce Derby plant under the pretext of learning maintenance procedures. In reality, they are there to observe manufacturing tolerances, heat treatment cycles, and assembly techniques that no blueprint will ever reveal. Stalin reportedly quips to his Politburo, "What fool will sell us his secrets?" Yet the sale proceeds. British intelligence has no hard data on Soviet manufacturing capacity or military intent. Only 1946 diplomatic assurances that the engines are for research and civil aviation. Attlee's government does not consult the Air Ministry or the Chiefs of Staff before approving the licenses. The assumption is simple. Even if Moscow tries to copy the Nene, Soviet foundries lack the precision casting and heat-resistant alloys required to produce turbine blades that survive sustained military power without cracking. The first 25 engines arrive in the USSR early 1947, crated and intact. Vladimir Klimov, lead Soviet jet engine designer, is handed the Nene samples and given a directive: replicate them for mass production. His OKB-45 bureau disassembles the first engine in a Moscow workshop, cataloging every component. No blueprints, no manufacturing drawings, no alloy specifications, just 25 physical examples. Klimov's metallurgists begin spark testing turbine blades to guess nickel and chromium content. His machinists measure tolerances with calipers and micrometers, trying to infer casting techniques from surface finish. The task is reverse engineering at industrial scale, and the clock is already running. Stalin expects prototype engines within months and production within 2 years. Early 1947. Klimov's team photographs every blade, every combustion chamber, every fuel nozzle. They build wooden mock-ups to test assembly sequences. The centrifugal compressor, a single radial impeller spinning inside a scroll casing, is mechanically simpler than the multi-stage axial designs Germany tried during the war, but it demands precision machining Soviet factories have never attempted. The turbine disc must withstand sustained temperatures above 1,000 degrees Celsius without warping. If the alloy composition is wrong, blades will crack after a few hours of operation, turning every fighter into a single sortie glider. Klimov begins a parallel effort: trial castings, iterative testing, and acceptance that early engines will fail. The goal is not perfection, it is production. Klimov's metallurgists face a problem no Western firm would tolerate: replicate a high-temperature nickel-chromium alloy using only spark test spectrography. They grind a turbine blade against a grinding wheel and analyze the color and pattern of sparks to estimate alloy composition. Mnemonic contains roughly 20% chromium and trace amounts of titanium and aluminum for creep resistance. But Soviet foundries lack equivalent superalloys. Early prototypes use a cobalt-nickel substitute that cracks under sustained military power. Time between overhauls for the first RD-45 engines, the Soviet designation for the cloned Nene, is 75 hours, compared to over 100 for the British original. Klimov accepts the trade-off. Soviet doctrine values surge capacity over individual engine longevity. To compensate for material deficiencies, Klimov's team enlarges the combustion chambers and increases turbine disc diameter. Airflow rises from 41 kilograms per second in the Nene to 45 kilograms per second in the improved VK1 variant. The larger impeller diameter forces a wider fuselage on any fighter that mounts it, but the centrifugal compressor tolerates altitude and temperature variation better than early axial designs, preserving thrust at extreme altitude. The VK1 produces 5,950 pounds of thrust, 19% more than the original Nene. It is heavier, less refined, but more powerful. Klimov has turned a British commercial engine into a Soviet weapon. Factory number 45 in Moscow begins mass production in 1948. Workers learn to cast turbine discs in batches, accepting a higher scrap rate than any Western plant would tolerate. Inspectors pull random engines from the line and run them to destruction, iterating fixes as production scales. Early RD-45s suffer turbine cracking. Engineers respond by slightly reducing maximum RPM and accepting shorter overhaul intervals. By late 1948, the first production MiG-15 fighters fly with RD-45 engines. The VK-1 follows within months, incorporating incremental improvements. Over the next decade, more than 30,000 copies roll off Soviet, Polish, and Chinese assembly lines, far surpassing total Rolls-Royce Nene production. Britain sold 25 engines. The Soviets built an air force. The MiG-15 airframe is designed around the VK-1's wide centrifugal compressor. The fuselage is 1,258 millimeters in diameter, noticeably fatter than the slimmer F-86 Sabre, which uses an axial flow engine. Swept wings and a high tail give the MiG exceptional high-altitude performance. Empty weight is 3,600 kilograms. With full fuel and ammunition, the VK-1's 26.5 kilonewtons of thrust produce a thrust-to-weight ratio of 0.92. The MiG climbs faster than any Western fighter except the Sabre, and at altitudes above 25,000 feet, it climbs faster than the Sabre too. Mikoyan's design bureau has built a high-altitude interceptor optimized for slashing attacks on bomber formations. The question is, where and when it will first be used. 30 November 1950. A U.S. B-29 Superfortress bombing an airfield near the Yalu River is attacked by an unidentified fighter closing at 680 miles per hour. The Superfortress gunners cannot track the target. It is moving too fast for their manually aimed turrets. F-80 Shooting Star escorts, cruising at 490 miles per hour, cannot intercept. The attacker makes a single slashing pass and breaks away vertically, climbing out of gun range in seconds. Intelligence confirms the impossible. Soviet-piloted MiG-15s, powered by engines the West did not know the USSR could produce, operating from sanctuary bases in untold Manchuria. The Korean War has just become a jet war, and the jet carrying a British engine. Intelligence identifies the threat. MiG-15s operating from Antung and other Manchurian bases, rotating Soviet pilots through combat tours under strict orders to avoid flying over water or south of the Chongchon River. Capture of a Soviet pilot would expose direct USSR involvement, so the rules of engagement create a sanctuary. The MiG's 5,950 pounds of thrust versus the F-80's 5,400 pounds means the swept-wing fighter dictates engagement altitude and geometry. U.S. pilots begin calling the northwestern corner of North Korea MiG Alley. Strategic Air Command faces a new problem. The B-29 Superfortress, which flew daylight raids over Germany and Japan without prohibitive losses, cannot survive an airspace contested by jets that climb faster and hit harder than anything in the piston engine era. 12 April 1951. 39 B-29 Superfortresses, escorted by F-86 Sabres, approached the Yalu River to bomb bridges near Sinuiju. MiG-15s dive from 40,000 feet, slashing through the formation faster than the bomber gunners can traverse their turrets. 3 superfortresses are shot down. 7 more are damaged beyond immediate repair. It is the first large-scale jet-on-jet battle, and the result is unambiguous. The piston-era bomber doctrine, tight formations relying on mutual defensive fire, does not work against jets that close at Mach 0.9 and fire 37mm cannon. Black Thursday forces Strategic Air Command to reconsider every assumption about daylight penetration raids. The MiG-15, powered by a cloned British engine, has rewritten the rules. 23 October 1951. 9 B-29s raid Namsi Airfield, escorted by F-84 Thunderjets. Coordinated MiG attacks intercept the formation. 8 of the 9 superfortresses are destroyed or damaged beyond repair. Gunners fire thousands of rounds but score no confirmed kills. The MiGs are simply too fast, closing and breaking away before defensive fire can converge. Black Tuesday ends the debate. FEAF Bomber Command immediately cancels all daylight missions north of Pyongyang. The strategic bombing doctrine that won World War II is now impossible in MiG Alley. The B-29 shifts to night-only raids, and even those will soon face MiG night fighter regiments. The catalyst is complete. Britain's exported engine now powers a weapon system that has forced the United States to abandon daylight air superiority. The MiG-15's dominance above 25,000 feet is a product of physics, not pilot skill. Thrust to weight governs the climb. The MiG-15 BIS, with an empty weight of 3,600 kilograms and a VK-1 producing 26.5 kilonewtons, achieves 0.92 thrust to weight when loaded with fuel and ammunition. The F-86E Sabre, empty weight 4,100 kilograms, and a J-47 engine producing 26.3 kilonewtons, achieves 0.86. That 6% difference means the MiG accelerates from 25,000 to 50,000 feet faster than the Sabre. In a vertical zoom climb, the MiG reaches sanctuary altitude before the Sabre can follow. Soviet pilots exploit this, dive for a firing pass, then zoom back to altitude, forcing the Sabre to fight on MiG terms. Service ceiling amplifies the advantage. The MiG-15 ceiling is 50,850 feet. The Sabre's is 49,600 feet. Soviet pilots climb into sanctuary above the merge, where the Sabre cannot follow without bleeding airspeed and losing maneuverability. From that perch, they dive for a single firing pass, boom and zoom in reverse, then zoom back to altitude before the Sabre can reverse the engagement. The tactic forces U.S. pilots into a defensive posture. They must accept the first pass and survive it, then exploit the Sabre's advantages in the transonic regime where the MiG loses stability. The altitude gap is only 1,250 feet, but in jet combat, that is enough to dictate who controls the engagement. The VK-1 centrifugal compressor is the reason the MiG's fuselage is wide, 1,258 millimeters in diameter versus the Sabre's slimmer profile. The centrifugal design uses a single radial impeller to compress air, forcing a larger diameter casing than the multi-stage axial compressor in the Sabre's J-47 engine. But the wide impeller tolerates altitude and temperature variation better than early axial stages, which can stall if inlet airflow becomes uneven at extreme altitude. The result? The VK-1 preserves thrust at 50,000 feet, where axial engines begin to lose efficiency. The wider fuselage creates more drag, but at high altitude, where air density is low, the drag penalty is small. The centrifugal compressor is mechanically simpler, more forgiving, and ideal for a high-altitude interceptor. The MiG-15 carries one 37mm N-37 cannon, firing at 450 rounds per minute, and two 23mm NR-23 cannon, firing at 650 rounds per minute each. Total ammunition? 40 rounds for the 37, 160 for the 23s. 1 or 2 hits from the 37 can sever a B-29's control surface or destroy an engine. The cannons are devastating but slow firing, and limited ammunition penalizes snapshots. The F-86 Sabre carries 6 50-caliber M3 Browning machine guns, each firing at 1,200 rounds per minute. a combined rate of fire over 7,000 rounds per minute. The Saber's radar-ranging gun sight compensates for human deflection error, giving pilots an accuracy edge the MiG lacks. High rate of fire suits tracking a maneuvering fighter. Heavy cannon suits slashing attacks on bombers. Above Mach 0.86, the MiG-15 suffers directional snaking. The nose yaws left and right. And at Mach 0.93, the aircraft experiences nose-up pitch that is nearly impossible to counteract. High-speed gun tracking becomes impossible. Pilots must slow down to aim accurately. The F-86 Sabre remains stable through transonic dives, allowing pilots to force MiGs into speed regimes where the Soviet jet loses control authority. This stability advantage is a product of the Sabre's all-flying tail and refined aerodynamics, developed through years of wind tunnel testing. Sabre pilots learn to exploit the MiG's transonic instability, bait the MiG into a high-speed dive, then outmaneuver it below Mach 1. The MiG is faster in a climb, the Sabre is more controllable in a dive. Tactics are written around those constraints. Summer 1951. The Soviet 64th Air Defense Corps deploys 3 fighter divisions to forward bases at Antung and Tungfeng, sharing ramps with Chinese MiG regiments. USAF intelligence counts approximately 500 MiG-15s versus 2 F-86 squadrons, fewer than 90 Sabres. Soviet pilots include World War II aces, Nikolai Sutyagin, credited with 21 kills including 9 F-86s, and Yevgeny Pepelyev, credited with 23. They fly under strict orders: remain north of Pyongyang, avoid the Yellow Sea, and never allow capture. If a Soviet pilot is shot down over UN-held territory, the political cost would be severe. The numerical imbalance forces U.S. planners into triage. Sabres escort B-29s, or they sweep MiG Alley, but not both. Soviet MiG tactics rely on regimental formations, 40 to 60 jets stacked in altitude, vectored onto inbound raids by ground-controlled intercept radar at Antung. Chinese and North Korean pilots, with fewer than 50 hours of jet time, fly standing patrols and rarely engage unless they have altitude advantage. The experienced Soviet pilots take the high perch, diving through U.S. formations and zooming back to sanctuary. If Sabres are pulled to escort B-29s, MiG trains sweep the interdiction corridor unchallenged, forcing fighter bombers to jettison ordnance and abort missions. The numerical advantage is not just aircraft, it is control of airspace. The Sabres can contest individual engagements, but they cannot be everywhere at once. Sabre pilots adapt. They cannot outclimb the MiG above 25,000 feet, so they force engagements into the transonic regime where the MiG loses stability. They fly in pairs, using mutual support to survive the first Soviet diving pass, then counterattack as the MiG zooms back to altitude. The radar-ranging gun sight gives them an accuracy advantage. Lead computing optics calculate deflection automatically, allowing pilots to concentrate on maneuvering rather than aiming. Even so, the kill ratio favors the Sabre only when Soviet pilots make mistakes, diving too low, extending too far, or dogfighting instead of zooming away. The numerical imbalance means every engagement is a calculated risk. Sabres hold the line, but they do not control the sky. December 1951 through January 1953. B-29s shift to night-only raids, using shore-and radar navigation to bomb through cloud and darkness. Soviet MiG night fighter regiments respond, deploying La-11 propeller fighters and radar-equipped MiG-15s to contest the nocturnal missions. Losses climb again, comparable to Black Tuesday according to FEAF records. By early 1953, superfortresses abandon even nocturnal missions to MiG Alley, except in poor weather when Soviet GCI radar cannot vector interceptors accurately. Strategic Air Command's bomber doctrine, the foundation of post-war U.S. air power, has been rendered unworkable by a jet fighter powered by a reverse-engineered British engine. The climax is not a single dogfight. It is the systemic collapse of bomber formations as a viable strike platform in contested airspace. July 1953. Armistice. The United States Air Force claims 792 MiG-15s destroyed versus 78 F-86 losses, a 10-to-1 ratio that becomes official doctrine for decades. Declassified Soviet records tell a different story. 335 Soviet-piloted MiGs lost, plus 224 Chinese. The true overall ratio is closer to 1.8 to 1. When only Soviet pilots flew, the ratio narrows to 1.3 to 1. The Sabre held the line, but the margin was far thinner than Cold War propaganda suggested. More importantly, the strategic result is unambiguous. B-29 daylight raids north of Pyongyang were permanently curtailed. The bomber that won World War II could not survive in MiG Alley. The piston-engine B-36 and B-50 bomber programs are truncated. Strategic Air Command accelerates development of the B-52 Stratofortress, a jet-powered bomber explicitly designed to outrun MiG interception at altitude. The B-52's 8 Pratt & Whitney J-57 turbojets produce a combined thrust of 68,000 pounds, enabling sustained cruise at 40,000 feet and 560 miles per hour, fast enough to complicate intercepts by first-generation jet fighters. The MiG-15's success over Korea proves that future bombers must be jets, not piston aircraft. The cloned Nene engine has rewritten U.S. procurement priorities and forced a multi-billion-dollar shift in strategic bomber design. Britain sold 25 engines. The ripple effects reshaped a generation of air power. 1958. Whitney Straight, Rolls-Royce deputy chairman, visits Beijing on a trade mission and discovers Chinese-built MiG-15s powered by unlicensed copies of the VK-1. The VK-1 is a copy of the Nene. The Chinese engine is a copy of the copy. Rolls-Royce begins pursuing unpaid license fees through international courts, citing the 1946 Non-Military Use Clause. The USSR refuses to recognize any claim, arguing that the wartime alliance implied permission and that the contract language was unenforceable. Britain's Foreign Office declines to escalate the dispute into a diplomatic confrontation. The legal pursuit drags on for years. Rolls-Royce recovers 0 royalties. Every future adversary notes the precedent. Stealing British military technology in the late 1940s carried no financial or diplomatic cost. The failure to enforce the contract sets a template for Cold War technology transfer. The USSR demonstrates that Western export controls can be bypassed through reverse engineering, that wartime alliances do not create enforceable post-war obligations, and that international courts cannot compel a superpower to pay license fees. Britain's Labour government prioritized export revenue in 1946 because the country was broke. The cost of that decision cannot be measured in unpaid royalties alone. It is measured in the redrawing of tactical doctrine, the redesign of strategic bombers, and the recognition that air superiority is no longer a Western birthright. The Nene export was not treachery. It was a miscalculation, grounded in the belief that Soviet metallurgy could not replicate mnemonic turbine blades. That belief was wrong. The MiG-15 remains in frontline service until the 1970s. Over 15,000 are built in the USSR. Licensed copies roll off assembly lines in Poland, Czechoslovakia, and China. The design is exported to 39 countries, serving in air forces from Egypt to North Vietnam. Its success establishes the Soviet Union as a credible aerospace power, ending the assumption of permanent Western air superiority. The MiG-15 forces the West to accelerate fighter development. The F-100 Super Sabre, the Hawker Hunter, the Mirage 3. Every subsequent Western fighter is designed with the knowledge that the adversary can field jets as capable as their own. That knowledge begins in Korea, powered by a British engine sold for commercial profit. The MiG-15's performance over Korea accelerates Western fighter programs that have been moving at peacetime pace. The F-100 Super Sabre, the first production fighter capable of level supersonic flight, enters service in 1954. 3 years faster than pre-war timelines projected. The Hawker Hunter, Britain's answer to the MiG threat, flies in 1951 and enters squadron service by 1954. France begins development of the Dassault Mystère, which evolves into the supersonic Mirage series. Each program is driven by the same requirement: match or exceed the performance of a Soviet jet powered by a reverse-engineered British engine. The technology transfer that began with Stafford Cripps's signature in 1946 forces the West into a sustained arms race that defines the next 2 decades of fighter development. The doctrine shifts are permanent. Strategic bombers will no longer fly unescorted daylight missions into contested airspace. Fighter escorts become mandatory, and escort range dictates strike radius. Air superiority is no longer assumed. It must be fought for and maintained, mission by mission. The U.S. Air Force rewrites its fighter tactics manuals, emphasizing high-speed maneuvering and mutual support. The RAF incorporates lessons from Korea into its own training, recognizing that the next air war will be fought against jets, not piston aircraft. The B-29 Superfortress, the symbol of strategic air power in World War II, is retired from frontline service by 1954. Its successor, the B-52, will never fly a daylight penetration mission without fighter cover and electronic countermeasures. The MiG-15 ended an era. The human cost is harder to quantify. U.S. and UN aircrew losses over Korea include hundreds of B-29 crewmen killed or captured when their bombers were shot down by MiG-15s. Soviet pilots rotated through combat tours, many never acknowledged by their government until decades after the war. Chinese and North Korean pilots, undertrained and outmatched, suffered disproportionate losses. The F-86 pilots who held the line flew outnumbered, constrained by rules of engagement that forbade pursuit into Manchuria, watching MiGs escape to sanctuary after every engagement. The cloned Nene engine did not just change procurement or doctrine, it changed the calculus of survival for every pilot who flew into MiG Alley. That human cost is the price of the 1946 export decision. The final ledger. Britain sold 25 Rolls-Royce Nene engines to the Soviet Union in 1946 and 1947, believing Soviet metallurgy could not replicate them. The Soviets reverse-engineered the Nene into the RD-45 and VK-1, producing over 30,000 copies that powered MiG-15 fighters in Korea and beyond. Those fighters forced the United States to abandon daylight strategic bombing, accelerated Western jet fighter development by years, and established the USSR as an aerospace peer. Rolls-Royce recovered 0 royalties. The contract included a non-military use clause. It was ignored. The precedent was set: technology theft without consequence. The story begins with Stafford Cripps signing an export license and ends with a generation of pilots fighting in the shadow of that signature. This is the full supply chain of air superiority.